You know that phone you've got in your pocket? I mean, have you ever really stopped to think about it? That little thing is way more powerful than the supercomputers that put people on the moon. So how on earth did it get so powerful? Well, today, we're going to pull back the curtain on the hidden story inside our devices. It's a story about hitting dead ends and then finding these absolutely brilliant ways around them. Let's jump in.
For like decades, there is this rhythm to tech that we all just got used to. Every year or so, computers would get ridiculously faster. We all just took it for granted. But then, right around the mid-2000s, that incredible rocket ship of progress kind of hit a speed bump. So what happened? Why did the race for pure raw speed just change course?
Okay, so to really get what changed, we have to look at the old way of doing things. This was an era that was all about one big idea for making chips faster, an idea that eventually slammed right into the hard limits of physics.
So the big trick back then was something called instruction-level parallelism, or ILP. Honestly, the best way to think about it is to imagine a single genius chef in a kitchen. Now, to get dinner on the table faster, you don't hire more people, you just teach that one genius to chop veggies, stir a pot, and check the oven all at the same time. For years, that's what engineers did. They just kept making that one chef smarter and faster.
But here's the thing. That genius chef started to overheat. And I mean that literally. The faster and more complex they made that one single processor core, the more power it guzzled, and the more heat it pumped out. We got to a point where we just couldn't cool the thing down anymore. The single chef kitchen had reached its absolute physical limit.
So if you can't make your one genius chef any faster without burning the whole kitchen down, what do? Well, the answer completely changed computing forever. You hire more chefs.
And this right here is the big pivot, moving from that genius chef model to what you could call the coordinated kitchen model. Instead of one super complex do-it-all core, engineers started putting multiple simpler cores all on the same chip. These are what we call chip multiprocessors. Suddenly, it wasn't about how fast one chef was. It was all about how well the whole team could work together.
And bam, just like that, the multi-core era was born. This is the fundamental reason why that smartphone in your hand has a dual-core or a quad-core or maybe even an 8-core processor. It's the direct result of engineers hitting that wall and being forced to completely rethink their entire strategy.
Okay, but as anyone who's ever been in a group project knows, just adding more people to the team doesn't magically fix everything. In fact, it creates a whole new world of problems, all centered around coordination and, just talking to each other.
So this was the next giant puzzle for engineers to solve. How in the world do you manage this new team? How do you make sure all these processor cores are working together like a well-oiled machine, instead of just tripping over each other and creating total digital chaos?
This kicked off a whole new list of engineering headaches. One of the biggest was this thing called cache coherence. So go back to our kitchen. Imagine all our chefs are working from the same master recipe book. If one chef decides to change a measurement, how do you make absolutely sure that every other chef gets that update instantly, so they don't all ruin the final dish? That, in a nutshell, is cache coherence.
A huge part of the solution was creating a really smart memory system. Think of it like this. Each core, each chef, gets its own tiny, super-fast personal fridge. We call that the cache, for ingredients it needs right now. Then they all share access to a giant walk-in freezer, that's the RAM, for everything else. Figuring out how to manage what's in the fridge versus what's in the freezer is what keeps the whole kitchen from falling apart.
All right, so once engineers kind of got the hang of this multi-chef kitchen, they had another aha moment. They realized, you know what? Not every cooking task is the same. Chopping onions is a totally different job than decorating a fancy cake. So why should every single chef be identical?
This led to the next massive shift, from what we call homogeneous cores to heterogeneous cores. So instead of a team of identical twins, chip designers started building a team of specialists. On your phone, this actually means you have a few big, powerful performance cores for heavy-duty stuff like gaming, and then a bunch of smaller efficiency cores that just handle background tasks without torching your battery life. And then you have the ultimate specialist, the graphics processing unit, the GPU. If a CPU is like a small team of master chefs who can cook anything, a GPU is like an army of thousands of line cooks who only know how to do one simple thing, say chop onions, but they can all do it at the exact same time. This massive parallelism, that's their superpower. And that superpower is the secret sauce behind anything that involves tons and tons of repetitive math. We're talking about rendering the millions of pixels that make your video games look so real, or training the gigantic neural networks that power modern AI.
But this whole trend of specialization, oh, it did not stop there, not even close. It has brought us to the absolute cutting edge of chip design, where we now build processors that are masters of just one single job.
So, welcome to the latest chapter in our story, the world of domain-specific architectures, or DSAs. The idea here is simple. Build a chip that does one thing and one thing only, but does it with an efficiency that is just off the charts.
And trust me, these things are everywhere now. Google has its own TPU that's just for machine learning. Microsoft has catapults to make its cloud services faster. And chances are, you've got one in your phone, like Google's Pixel Visual Core, a chip whose entire existence is dedicated to making your photos look absolutely stunning. They're custom-built tools for very specific jobs.
So when you boil it all down, it's really about this trade-off. Your general-purpose CPU, that's your master chef. It's super flexible, can do anything, but it's not always the most efficient. The GPU, that's your specialized chef. And the DSA, that's like a custom-built machine that only makes perfect pasta. It can't do anything else, but boy, it makes pasta way faster and using less energy than any human chef ever could.
And this leads us to a really fascinating final question. We've gone from one genius core to this whole team of specialists. So as what we need from our computers gets more and more specific, from AI to incredible photography, are we heading toward a future where that general do-it-all computer is just a thing of the past, replaced by a collection of hyper-specialized tools? The next time you pick up your phone, you'll know it's not just one genius in there, it's a whole kitchen full of them.